let's have a closer look at simple harmonic motion. We have some special positions here that are represented and would like to examine them more closely. This horizontal spring is oscillating between this position that's given by x equal a and this position here that's given by x equal minus a. The equilibrium position is represented in blue here as x equals 0. So it is oscillating back and forth between here and here. Okay, so this is representing one position, the position at equilibrium, the position when the spring is compressed to a maximum. Equilibrium again, the spring is not compressed and the spring stretched to a maximum. As you recall, we can express the position as a function of time, velocity as a function of time, and acceleration as a function of time by either this set of equations or this set of equations. The only difference is the value of phi that we choose. For example, if we choose this position here as the position corresponding to t equals 0, then at t equals 0, x should be equal to a. So then in this expression, x of 0 should be equal to a. So a sine of 0 plus phi. The sine has to be equal to 1. For that to be equal to 1, phi has to be equal to pi over 2, or 90 degrees. The velocity has to be equal to 0. At the maximum position, when the spring is stretched to a maximum, there is no velocity for the mass. It momentarily stops. So this expression should give us a velocity equal to 0. For that to be 0, the cosine should be equal to 0. And in this case, cosine of pi over 2 is 0. The acceleration has to be a maximum acceleration in magnitude, but its direction has to be in the negative direction. Remember Hooke's law. The only force acting on the spring along the x direction is the spring force, which is minus kx. Notice here that I wrote it x as a function of t, since x changes. And that should be equal, since it's the only force acting on the mass along the horizontal, applying Newton's second law of motion, that should be equal to m times a. And again, the acceleration changes here. That's why it is a as a function of t. So at this position, we have maximum amount of stretching, so the maximum x, so I should have the maximum acceleration. And that's correct here as well, since the sine of pi over 2 is going to give me a 1, so that gives me the acceleration as minus a times omega squared. So that's perfect. Now, if I were to use these equations instead, the phi has to be equal to 0, because the cosine of 0 plus 0 is equal to 1. So that gives me a here, and then sine of 0, 0, so that gives me 0 here, and 1 here, that gives me minus a omega squared. So in brief, if I use phi equal pi over 2, I'll use this set of equations. If I use phi equal to 0, I use this set of equations. Okay, let's go back to the special positions. So x equal a, v equals 0, a is equal to minus a max. What about when the mass passes by the equilibrium position? So in that case, x is equal to 0, since it is passing by the equilibrium position, since the spring is not compressed. Now, if x is equal to 0, the acceleration is also equal to 0. Remember, look at the relationship between acceleration and x. Acceleration is just minus k over mx, or the acceleration is minus omega squared x of t. So the acceleration would be equal to 0. Now the velocity here should be at a maximum value, but since it's moving back towards the compressed position, or moving in the negative direction, it should be minus. So the velocity is minus Vmax. So again, as the mass passes by the equilibrium position, we have x equals 0, v minus Vmax, which is a omega, minus a omega, and a, the acceleration is 0. Now remember, by going from here all the way here and then back to here, that's a full period. So in other words, if this is a period, this is half a period, that's a quarter of a period. So after another quarter of a period, we are with the spring compressed to a maximum. So the x position is equal to minus a. It temporarily stops there since it is compressed to a maximum, so the velocity is equal to 0. And the acceleration, remembering that the acceleration is minus omega squared x, so the acceleration is going to be at the maximum value. But it's going to be a positive value since the force in this case is going to accelerate the mass in the forward direction. In the equilibrium position here, again, the x position is 0, the acceleration is 0, but opposite to this position, the velocity is positive since my mass is moving forward. So my velocity is Vmax. And then here we go back to our initial position and we recycle back.